Hello guys, I'm Siddhant Mukherjee. Today we'll discuss about the spatial econometrics analysis. We know that spatial econometrics is somehow different from mainstream econometrics analysis. It captures the locational parameters. Sometimes if we discuss about the geographical parameters in the mainstream econometrics analysis, the spatial econometrics is important for analyzing the behavior of the measuring the locational estimators. It is basically the captures the locations. So spatial econometrics is basically the region using regional science, and it is also in quantitative geography, quantitative geography. Okay. Now in this spatial econometrics relations, we'll discuss about what is spatial econometrics and what is the difference from the spatial relations is mainstream econometrics relations. So in this section, we'll try to understand that spatial relations in the spatial econometrics. We should know about the spatial relations, spatial relation, spatial dependence, and spatial structure. In the cross-sectional data, we basically uses in the cross-sectional data we basically uses the quantitative geographical parameters and geographical locations in the regional sciences. So the cross-sectional data somehow related with the location, and in the normal econometrics analysis cannot captures this relation in locations somehow that if unemployment rate, look, unemployment rate in West Bengal somehow is locationally, is it locationally depend on the unemployment in Bihar, or it is somehow unemployment is of West Bengal is somehow locationally related with Odisha, is it? But normal regressions model, normal cross-section models can captures these locational structures. Suppose Suppose that I am going to a blank page for better understanding. Suppose that the cross-sectional data uh, is somehow related to the location. So if yi equal to f of yj, suppose households I and j are located at different spaces. I is not equal to j. They are different. I is different from J. I is household locations, J is another household locations. Suppose that in the mainstream econometrics fails to capture the this kind of relationship, right? So as locations are closed, consumption patterns are very closed. Suppose the consumption's pattern in Odisha is somehow uh, related with the uh, West Bengal, or the boundary states of Odisha like Andhra Pradesh, Chhattisgarh, or the but the consumption pattern of Bengal is how related with the consumption pattern of Rajasthan. Let us see. Then suppose J is the consumption pattern of Rajasthan, I is the consumption pattern of West Bengal. But there is the locational difference is far away. So the capturing time needs more, right? So the unemployment, suppose unemployment is a very big issues currently in India, and unemployment is locationally location of the unemployed person who is employed or who is unemployed, and their consumption pattern is how related with the consumption pattern of Rajasthan with suppose Gujarat. The relationship between the consumption pattern of a unemployed person or an employed person in Rajasthan and Gujarat are locationally kind of correlated. Right. Now, the unemployment employment in the locational changes employment in a particular space can be depend on the location in another place. It is not captured by the mainstream econometrics. So what should we need to do? Suppose that in the normal way, what we know about the normal regression analysis in the classical economics or classical econometrics. In classical econometrics, or there is a Gauss Markov assumptions, right? There are some assumptions of classical assumptions we know as a Gauss Markov assumptions, right? So it is Gauss Markov assumptions. What is it says? This said that let us take on equations, right? Uh, Let us take an equation of yi equal to beta prime xi plus epsilon I, where yi is the independent variable, xi is the dependent variable, beta is the slope parameter, epsilon is the error. Okay, ratios. So expectations of Cosmarkov assumption, what is said? Expectations of epsilon I is equal to 0, expectations of epsilon I square equal to sigma square, expectations of epsilon I, epsilon j is equal to 0. 0 mean constant variance is the 0 mean constant variance is the main assumptions of the Cosmos assumptions. So now in there is another assumption, right? It is known as non autocorrelation relationship. Non autocorrelation. So it is what it is said that covariance of epsilon I, epsilon j equal to 0. Obviously, that means covariance between yi and yj is obviously 0. Means yi has no effect in f of y j. So there is no autocorrelation relationship presence. There is no relationship between the consumption pattern of I region with the consumption patterns of jth regions. No this means no spatial dependence. No spatial dependence. Okay, now we come to our PBs. What it says, look, in a spatial regression or a spatial econometrics or spatial economics, what is it basically says? It basically captures the regional estimations. Suppose this is agricultural dependencies on the regional sectors of Africa. It is a research proposals given by the reference of books. It's given last that in research paper it collect these maps of the uh, cultivated lands for agriculture and the relationship between the land cultivation, agricultural methods, agricultural productions, and the effects of weather, regional weather. So we can see that the areas of South Africa's is red lighted areas. There is some red lighted areas in there, some red lights there. The consumption patterns in different countries are regionally affected, right? Suppose in a state is located besides B state, but A state is far away from M state. So A state's agricultural productions have a special relationships with B state's agricultural productions. It's more similar, right? But A state's agricultural relationship is somehow different from the M states. Is it somehow different from the M states agricultural productions or not? It is our main concern, and this relationship of the econometrics is captured by spatial econometrics, and this is right. And now we're coming to 1 second, and there's a spatial dependence. The spatial dependence is actually spatial dependence models is somehow related on spatial autocorrelation, spatial autoregression, spatial moving average, spatial ARMA, autocorrelation, autoregressive moving average process. Some we basically in this video lecture series we basically captures the time series properties or time series analysis of the spatial regression model. Now, first of all, the things is important for identifying a spatial relationships is most importantly number one is spatial lag, and number two is spatial autoregression. Spatial autocorrelation is basically not only depends on the theoretical structures but also depends on the some empirical estimated processes like specifications of the model, right? Problem of estimations, which is doing in the next series of video lectures, and testing of for spatial dependence. Right. Now, if we quantifying a location, spatial econometrics basically deals with the locational parameters we discussed in the first. Now, spatial location is measured conventionally with the distance of another spatial aspect, spatial information of contiguity. What is the contiguity relations? We now discuss with that. Suppose, suppose this is some 1, 2, 3, 4, 5 are different regions. Okay. Now, region 1 has a boundary location with region 2. Region 3 has a boundary locations of region 5 and region 4. Also, region 4 has a boundary locations with region 3 and region 5. And also, region 5 has the boundary locations with region 4 and 3. But region 4 has do not any boundary sharing with region 1 or region 2. 5 also. So, how we quantifying the locations? Number one is by distance, and number two is by neighborhood effect. Right. So location 1 has a common border with location 2. Location 2 has also a common border with location 1. Location 3 has a common border with location 4, location 5, and location 4 and 5 also doing the same. Now, by definition of a quantifying region, definition of locations, what is measures by the definitions of locations? Quantifying locations. Definition of locations means quantifying the locations in the spatial econometrics analysis. If there is a common border, say it is contiguity. If there is a common border, say it is contiguity. If not, no contiguity. Common border, contiguity, no common border, no contiguity. Okay, so contiguity relation express the terms of the matrix of spatials. If we terms by terms we spatially creating the regional matrix, we can form a regional matrix of this. Look, this is a regional matrix we can form. Okay, now in here we can form the matrix. Let's see with the relationships of the contiguity. Let it is region I and it is region J, and this is the contiguity of we can form this matrical forms. There is this is for J is 1, is 2, is 3, 4, and 5. For this I region 1, 2, 3, 4, and 5. So 1 and 1 has obviously no border. So this is considered as 0. 1 and 2 has relations. So this we consider 1. 1 and 3 has no relations. So 0, 4, 0, 5, 0. 2 and 1 has a regional sharing or contiguity. So we can give it 1. Region 2 has 0, 3, 0, 4, 0, 5, 0. 3 and 1, 0, 3, 2, 0, 3, 3, 0, 1 and 1. Because look, 3 and 4 is region sharing, has contiguity. Region 4, 1, 0, 2, 0, 1, 0, 1. And this is 5, 0, 0, 1, 1, 0. So this is a form of matrix, and the row represents the locations. If the relative positions with the others, then we said that 1 and 1 has no regional parameters, because how 1 and 1 has regional parameters, right? 1 and 2 has regional parameters, so it is 1, 1 and 3 has regional parameters, so it is 0, like this. So can you see one thing that hmm, the region 1 to this in this up to this, if we draw if we draw with another symbols, 1 to it is form a matrix, and look, this is from the another matrical forms, right? Hmm. So if for the n terms, what we do for the n terms, look, this is the whole matrix forms in the nth term with the nth terms. It is obviously a in cross in matrix. So wij, it is a whole form of wij, and wij equal to is called spatial weight. Right. Now, one thing for quantifying allocations. So, locational quantifications is an element of matrix wij is obviously taking a values. So it is kind of dumb variable type. So, w we consider wij equal to 1 if I and this wrong way. So, if wij equal to 1, you can say I and j has common border, and if it is 0, it's otherwise. So element of matrix wij taking its value 1 shows it's a presence of contiguity, and region has a common border, and elements of taking value of 0, it is means it is no contiguity, it is no sharing the common borders. The contiguity relations for each region shows the rows of the matrix, but it says in here. And in the terms of the rows of spatial map, what is W, capital W? We can further analysis, we can show its behavior as capital W. Okay. By quantifying allocations, the consecutive relations considers the examples of rock contiguity. For a region that shares a common border, sides with the region of interest, W I equal to 1. If I shares a boundary with J and Wi J is 0 with us otherwise. So 1 shares with boundary 2 is 1, others 0. So as 2 shares with boundary 1 and is 1 and others are 0. So in the standardized version of W, so we can say that sum of Wij equal to 1. Sum of Wij equal to 1. Right. To make the boundary parameters, we need the standardized weight matrix. And now we see that mm, the contiguity relationship is kind of symmetric, right? So how this process of Wij is equal to 1? If, right, W equal to the matrix 0 1 0 0 0 1 0 0 0 0 0 0 0 0.5 0.5, look at the picture, 3, this is 3, this is 5, this is 4. The sum of the contiguity, sum of the parameters, uh, so in row standardizations, the sum of Wij must be 1, so that for the row standardization, we need to do that. 0 0 0.5 0 0.5 and 0 0 0 point sorry 0.5 0.5 and 0. This is, And suppose the variable of locations y equal to locations of y1, y2, y3, y4, y5. Okay, there's a metrical forms. So if we see that, so wy, so wy equal to, look, wy is the 5 cross 5 matrix, and y is 5 cross 1 matrix. This 5 cross 5 is 5 cross 1, right? So this is what is the metrical structure for form this can be. Hmm, this is not. Hmm. And this is structures of this is also 5 cross 1. So the structures of the variables will be matrix structure will be y2, y1, 0, y2 into 0, y2 into 1, y3 into 0, y4 into 0, y5 into 0. So this is, you know, the matrix multiplication rules, I guess. So y2, y1, zero point 0.5, y4 plus zero point 0.5, y5, zero point 0.5, y3 plus zero point 0.5, y5, and zero point 0.5, y3 plus zero point 0.5, y4. This will be the whole matrix, and we can consider this as y star, right? So this is a 5 cross 1 matrix. This is 5 and this is 1. Yep. After this, we know that the matrix multiplication rules, right? So if two locations commons look, if two location covers a common location, it is called spatial effects. And after pre-multiplying the weight matrix, we get the locational effects. Understand? Now we do this like this. This row standardized matrix wi j equal to 1. This summation. Mind all this, and and this is a neighborhood effects. Cover that. Mm, Now we come to another structural forms of the weight matrix, of the uniform weight matrix. In this case, a spatial distance look, that is, we know that uh, for row standardizations, the summation of wij equal to 1 for row standardization implies that the boundness of the parameter space and the sum of all elements in the weight matrix is equal to the number of observations in, right? And for the specifications, uh, we can deal with some, look, summation of wij for j equal to 1 to n is 1. Suppose we define a weight matrix in a spatial form. It is a uniform weight. You can highlight this as much. It is uniform weight, right? For the uniform weight, a spatial matrix is the weight matrix is defined in these ways. Now the question come in mind is, what is D? I is the common border, we know that. And what is D? D is called threshold distance. if two common borders more than d, then it is a 0. So in this case, wij equal to I of I is a function, I functional dij is less than d divided by summation of the identical functions of I of dij is less than d. What is I? What is this I of dij? The I of dij is called indicator function. If the indicator function takes two common borders more than, if the value of the common borders is more than d, then it takes 0. Of dij is the indicator function and it take the value of 1. Okay, for this common uniform weight matrix. And if it the bilateral distance between two locations I and j is less than d, it takes the value of 0. Neither takes the value of 1 because we know that wij equal to 1 if the contiguity, if they have the contiguity, and if 0, no contiguity, right?